This program, ADCT, demonstrates analog sampling and reconstruction of a band-limited signal and allows one to demonstrate the effects of aliasing. The bottom panels show the time domain. The top panels show the frequency domain. The signal flow goes from left to right. We start by creating a triangle in the top left panel that represents x of f, the frequency response of the input. Either drag it out on the plot, use the slider, or enter a value in the edit box. The corresponding time function, x of t, appears here in the lower left panel. Select a sampling frequency, f of s, in the top middle panel, either by dragging in the plot, using the slider, or entering a value in the edit box. The transform of the sampled signal, xs of f, comprises replicas of x of f at multiples of the sampling frequency, which are marked by the little green triangles. For clarity of display, the amplitude of the transform of the sampled signal is normalized to 1. However, to be accurate, the amplitude of each replica should be scaled by the sampling frequency in hertz, which you do by checking this box. The lower middle plot shows xs of t, the sample time signal. The red triangles mark the actual times of the impulses in xs of t. As you increase the sampling frequency, the spacing of the transform replicas in the frequency domain gets wider and their amplitude increases, while in the time domain, the spacing of the samples decreases. The shaded region in the upper panel shows the frequency range of the ideal low-pass reconstruction filter that would be in an ideal D to A converter. This frequency range is always set to half of the sampling frequency. The output of the reconstruction filter is shown in these right panels, frequency response y of f on the top, and the time domain response y of t below. Clicking this control allows you to demonstrate how the output y of t is formed in the time domain. Each of the thin gray traces here represents the response of the ideal reconstruction filter to the corresponding impulse of xs of t. The sum of all these scaled and shifted sinc functions is the output y of t shown in the blue trace. As long as the sampling frequency is above the Nyquist rate, as it is here, there will be no aliasing. However, lowering the sample frequency will cause aliasing. To see this effect clearly, it's first useful to expand the frequency scale. And let's also unscale the amplitude. Decreasing the frequency below the Nyquist rate results in overlapping replicas of xs of f. The high frequency edges of the image replicas add to the lower frequency spectrum of the baseband signal, causing aliasing. Let's expand the frequency scale again. When filtered by the low-pass reconstruction filter, whose bandwidth is half the sample rate, the spectrum of the output signal shows aliasing. In the lower panels, the aliased time waveform is shown in blue, and the unaliased signal is shown in thin red. To mitigate the effect of aliasing, click this control to place an ideal analog anti-aliasing filter at the input to limit the spectral frequencies of the input to no more than half the sampling frequency. The output panels show the effect of applying this anti-aliasing filter in the frequency domain and in the time domain. You can now load a sound file, play it,
She sells seashells,
and also simulate what would happen as the result of sampling and reconstructing at various sample frequencies.
She sells seashells. She sells seashells.
Both with the anti-alias filter and without.
She sells seashells.
This program is one of a suite of programs that I have developed to explain DSP concepts to my students during lectures. There are now well over 24 programs covering many aspects of the material in the book, including complex exponentials and sinusoids, convolution, the DTFT, pole zero plots and their relation to frequency and impulse response, A to D and D to A conversion, including upsampling, downsampling, resampling, and aliasing, the design of many types of FIR filters and their application to the filtering of speech and other signals, the design of IIR filters, circular shift and convolution using the DFT, the discrete cosine transform, and the short-time Fourier transform. A selection of these programs is being made available to instructors who are currently adopting the book in their classrooms. For further information, please visit cambridge.org/Holton.